Hello students, in the last lecture we have discussed about the first application of Gauss theorem. Here we are going to discuss another application of Gauss theorem, that is electric field intensity due to infinite long straight uniformly charged wire. What I am saying, uniformly charged wire. How will you find out the electric field intensity due to infinite long straight uniformly charged wire? Here we are considering a uniformly charged infinite long wire. We are considering another imaginary cylinder called Gaussian surface of radius small r over this infinite long uniformly charged wire. It is of radius small r. And let us consider its length is small l. Now, what if we are taking a small area about it, that small area ds about it, in which electric field intensity is working outward, that is E, then electric flux may be given like d phi is equal to E dot ds, as we know that, and it may be given as d phi is equal to E ds cos 0 degree. This can be written like E ds. This might be question number 1. Moving further, what would be the total electric flux? But the total flux through the cylinder, through the imaginary cylinder, we can say that through the Gaussian surface is given as what is that? Phi is equal to line integral. Here what we are using, that is line integral of d phi, because we are talking about an infinite long straight uniformly charged wire. That's why we are taking this line integral. If we are talking about the surface, we'll use surface integral. This can be taken as line integral, and this can be considered like surface integral. So here what we are taking, that is line integral, that is d phi. Now we are putting the value, that is phi becomes E ds. E can be taken out, and this one is line integral of ds. What is the surface area of cylinder? If we know that, that is 2 pi rl, then phi becomes E dot 2 pi rl. This one is equation number 2. But we have one more thing. We have, by Gauss theorem, what we are having, that phi is equal to q upon epsilon naught. And we know that when left hand side is equal, then right hand side would also be equal. So by equation 2 and 3, what we are getting, that is E dot 2 pi rl would be equal to q upon epsilon naught. This can be written like E is equal to q upon 2 pi rl epsilon naught. But we have, what we are having, that is q by l is equal to lambda. This is called linear charge density. Then E can be written like E is equal to lambda upon 2 pi epsilon naught r. This would be your result. your result. So what you have studied, that is electric field intensity due to infinite long straight uniformly charged wire, that is d phi is equal to E dot ds. First of all, we are taking at infinite long straight wire, and we are considering a Gaussian surface like a cylinder, because wire is in shape of cylinder, as we know that. So here we are taking as cylindrical shape, that d phi is equal to E ds cos 0 degree, because it is acting on the surface and both are parallel to the n, that is d E ds, but the total flux through the Gaussian surface is given as that phi is equal to line integral of d phi. Here why we are using line integral, that is just we are talking about the length, that is why we are using line integral. And here we are putting the value, and what we are getting, that E dot 2 pi RL. But we have by the Gauss theorem, that is phi is equal to Q upon epsilon naught. So here what we are getting by equation 2 and 3, when we equate that equation, we are getting that E is equal to Q upon 2 pi RL epsilon naught. But we know that Q by L can be considered as linear charge density. So here we are putting the value, and what we are getting, we are getting the result, that is E is equal to lambda upon 2 pi epsilon naught R. Moving to our next topic, that is electric field intensity, that is electric field intensity due to uniformly charged thin spherical shell. First of all, we will talk about hollow sphere. Uniformly charged spherical shell. First of all, we will talk about hollow sphere. Here there would be two of the condition or three of the condition would be there, that we are taking a point inside the sphere, outside the sphere, and at the sphere. What I am considering here would be three of the condition. First of all, when we are taking a spherical surface, like it is having the radius of capital R, then we have to take three of the cases. The first case can be electric field intensity at a point outside the shell. What would be that? Now here what we are considering a spherical surface, and another a point we are considering outside the sphere, on which we have to find out that electric field intensity, how much electric field intensity is acting on that. So we are taking it as a small r distance from the origin, or you can say that from the center. So here what we are considering a Gaussian spherical surface. So what would be the electric flux on that? Electric flux, if we are taking the small flux on that, that is d phi, can be written like E dot ds, then it may be given like E ds cos 0 degree, that is d phi is equal to E ds cos 0 degree. We are doing the same thing what we are discussing in the last one, that is d phi can be written like E ds. This part is same in all that particular. So total flux is given by, how will you get? That is phi is equal to surface integral of d phi, and that can be written like surface integral of E ds. It can be written like E surface integral of ds, that is E. And here what is the total surface area? We are taking a point outside it, then we have to take the distance from this center to the point P. So what would be there? There would be 4 pi and a small r square, because the distance from the center to the point P is smaller. So we are taking it E dot 4 pi r square. So here what we are taking, that surface integral of ds can be written like 4 pi r square. that is phi is equal to equation number, this can be considered as 1, this can be considered as equation number 2. Moving further, but we know that by Gauss theorem, what we are having? We are having phi is equal to q upon epsilon naught. This can be considered as equation number 3. So what is there? That phi is equal to q upon epsilon naught. Now what we can do? We can do by equating equation 2 and 3, we get what we are getting here, that is E dot 4 pi r square would be equal to q upon epsilon naught. Then what is the value of E? E is equal to 1 upon 4 pi epsilon naught q upon r square. This would be the result of outside. What is that? Electric field intensity at a point outside the shell. Now moving for the next case, that case is electric field intensity. Second one case is what? Electric field intensity at a point on the surface of the shell. Now we were considering in the last one that the point is lying outside the shell. Now what we are considering? We are considering that capital R would be the shell, and one of the point we were taking outside the shell, but now it is at the surface of the shell. Then what would be here? There would be small r becomes capital R. Thus the result can be given as, that is E is equal to 1 upon 4 pi epsilon naught q upon capital R square. This would be your result at the surface, or you can say that at a point on the surface of the shell. Now the third one is that electric field intensity inside the shell. What would be the electric field intensity inside the shell? As we know that inside there would be no charge. That means the value of Q becomes 0. So what would be the electric field intensity? That would be E is equal to 1 upon 4 pi epsilon naught 0 upon r square, that becomes 0. That means we can conclude that electric field intensity inside the shell is always 0. Clear?